let's discuss about the formula that relates the d/t ratio and yield stress and inelastic buckling allowable compressive stress. So here you see the Fy is the yield stress of the tubular material and Fx is the inelastic buckling allowable compressive stress. d/t ratio is the dimensional ratio of the diameter d and the steel tubular section and thickness T of the section. Here breakdown of the formula, you can see d/t is the ratio of diameter to the thickness of the tubular section. It's a dimensional ratio that gives a measure of slenderness of the tubular structure. That's nothing but how much slender the tubular it is. Like a higher d/t means that it's more slender, while the smaller d/t it means that it's compact and robust. And d/t power 0.25 is the rising d/t to the power 0.5 reflects a nonlinear relationship between the geometry of the section to its diameter, thickness, and allowable compressive stress. The exponent 0.25 indicates that d/t increases, the effect on the compressive stress Fx is gradual, meaning that the inelastic buckling stress decreases at a decreasing rate to the diameter to thickness ratio increases. The term 1.64 acts as a baseline value for the ratio of Fx by Fy when d/t is equal to 1, meaning that for the very thick tubular section, the allowable compressive stress is close to the yield stress. The coefficient minus 0.23 shows the rate of reduction in the allowable compressive stress Fx as d/t increases. The negative value indicates that the tube becomes more slender. That means larger d/t, the inelastic buckling stress decreases. The physical meaning, we can see the yield stress of the tubular. This is the stress at which the material will begin to plastically deform. Beyond this point, the material will no longer return to its original shape after the load is removed and the permanent deformation occurs. The yield stress is a fundamental material property of steel. Fx is the inelastic buckling allowable compressive stress. This is the maximum compressive stress that the tubular section can withstand without experiencing inelastic buckling. Ratio Fx by Fy. That ratio describes how the inelastic behavior buckling allowable compressive stress compares to the material's yield stress. Let's see one thing like, alright class, today we are going to learn about the forces that can cause materials like steel to bend and break. This formula is used to calculate how much force a steel tube can handle before buckling. But who can tell me what buckling is? Isn't buckling when something bends and doesn't go back to its original shape? Exactly. When a material bends too much under pressure, it deforms permanently. But this formula helps us understand how much pressure a tube can handle before it buckles. But why do we need the formula? Why do we need the formula? Can't we just look at the tube and guess? Good question, Sophia. It's not that easy. We need a way to calculate it so that we don't guess wrong. If we guess wrong, the tube could fail under pressure. Let's break down this formula. Okay, first things first. Fy is the yield stress of the material, the point where the steel starts to permanently deform. Think of it like when you bend a paper clip too far and it stays bent. Oh, so Fy is the stress. The steel Fy is when the steel breaks its elastic limit. Exactly, Max. Fy is nothing but when the steel breaks its elastic limit. Now Fx is the inelastic buckling allowable compressive stress. A big term, right? What it really means is it's the maximum amount of compressive force the steel tube can handle before it buckles in a way that's irreversible. So Fx is the point where the steel tube collapses from too much pressure. Yes, that's right. And we need to know how much force a tube can handle before buckling because it's a critical part of the building structures like bridges or buildings. So what is d/t? Now let's look at the ratio d/t. This means the diameter to thickness ratio of the tube. So d is the diameter of the tube, t is the thickness of the tube. Exactly. If you make the tube thicker, the force it can handle before it collapses, like before buckling, goes up. If the tube is thinner, it's more likely to buckle under pressure. If the tube is thinner, it's more likely to buckle under pressure. So the larger the d/t ratio, thinner the tube, weaker it is against pressure, right? Yes, exactly. The more slender the tube, meaning the larger d/t, and the more likely it's to buckle because there's less material resisting that force. Let me plug in some numbers. If you have the tube and the diameter to thickness ratio of 40, which means it's thick, and yield stress Fy equal 250 MPa, What do you think happens to the allowable compressive stress? What do you think happens to the allowable compressive stress? Isn't the dBdt is a smaller number? Yeah, that would make the tube thicker, right? Yes, exactly. A smaller dBdt means that the tube is thicker. Let's calculate fx by fy. The x1.25 means that we take the fourth root of the power root of 40, which gives us about 2.8. Now let's plug that back in fx by fy, that's equal to 0.996. So the compressive stress is close to fy, which is 250. That means the tube can handle almost its full yield stress without buckling, right? Yes, exactly. Now let's try a higher dBdt value like 160, which makes the tube thinner. What do you think happens now? Let's plug in t by d equal to 160. So that gives us 3.5. So fx is now lower than before. Wait, does that mean the thinner tube can't handle as much pressure? Yes, as the tube gets thinner, that means larger dBdt ratio, the compressive stress it can handle before buckling decreases. The more under the tube, the more it will bend under pressure. So to prevent buckling, we want lower dBdt ratio, right? Exactly. The thicker tube, the better it can handle the pressure. That's why the formula is so important. It helps engineer to figure out how thick the tube should be for safety. But wait, if we make the tube too thick, doesn't that make it heavy and expensive? That's right. Engineers have to find a balance between making the tube strong enough to resist buckling, but not so thick that it's too heavy and costly. So is the goal to make the tube just thick enough to handle the right amount of force? Exactly. That's why the formula is so important. It helps engineers design the most efficient, cost-effective, and safe structures. They want to optimize the tube's thickness to handle the forces while keeping things lightweight and cost-efficient. So in a way, the formula helps us find a sweet spot between the strength and efficiency. You got it. It's all about finding that balance. And now you understand how engineers use this formula to make structures safe, strong, and efficient. So if I were designing a steel beam for building, I would use this formula to figure out how thick the steel tubes should be, right? Exactly. And if the tubes are too slender, you can calculate how much force they can handle before buckling. If they are too thick, you can calculate how much strength they have without being too heavy. It's all about making sure the structure doesn't break. Just make sure that the structure is safe. Yes, now you all have better understanding of how engineers use a formula like this to design a safer, stronger buildings. You are one step closer to being engineers yourself. What exactly does this formula mean? Why do we have this equation fx by fy? It's to describe how two forces interact based on the dimensions of the object. But what do you think happens when the dBdt changes? If the dBdt is like a ratio of size, does that mean it controls how much the force is distributed in different directions? The ratio tells us about the shape of the object, but what happens if the ratio increases or decreases? If it increases, does that mean the horizontal force becomes less important? Why does that happen?